All right, so a rational function up here is a function that can be written as the quotient of two polynomial functions, p of x and q of x, as long as q of x is not 0, because you can't divide by 0, and p of x and q of x have no common factors. So another thing to point out, these have to be polynomial functions, right? So they can't have things like exponents that are -1 or 1/2, right? These are still abiding by the rules that those are polynomial functions. And when there are common factors, we're going to have to factor and cancel before we start graphing. Those are going to create asymptotes and holes in our function. So here are just a few examples of 3 different rational functions. We don't know a lot about them right now, but we could think about their domain. So what would be an excluded piece of x terms, right, that I could never plug into this function because it would make the denominator 0? What x value would make my denominator 0? So it would make this function undefined. What would I put right there? What plus 1 will give me 0? -1, right? So x value cannot equal -1. So in the next rational function, this denominator is not factored, so I'm going to factor it. So I'm looking for the factors of -6 that add up to -1. So we should know from our study that that would be x minus 3, x plus 2. So when it's in factored form, I can see that the bad values for x are +3 and -2. And in this last function, what would you say? So if I plug in a value here, what's going to make the denominator 0? Someone tell me. Nope. +1, right? 1 minus 1 is going to give me 0. So this is like writing x minus 1 times x minus 1. 1 is going to make the denominator 0. So rational functions have places where the function is not defined. And that's different than polynomial functions, right? Polynomial functions were smooth curves, and I could use any value of x that I wanted. Rational functions are going to have places where you can't use certain values of x. So here's a quick summary of what we're going to look at over the next couple days. So there's a lot of steps to rational functions. So graphing a rational function can be tricky, but not if we carefully follow the same procedure each time. So first, we're just going to look at finding x and y intercepts. Then we're just going to look at finding all the asymptotes. So keep those 2 skills really separate in your head. How do I find x and y intercepts? How do I find asymptotes? And then if we want to find more points on the graph, all we have to do is plug in x values, right? Basically make a table of values, plug in x values. And then there's 2 major things to remember. These are functions, so they always need to pass the vertical line test. So for example, if you're graphing away and you graph part of your rational function up here, it should not be possible to have the other leg of your rational function underneath it, right? Because then it would fail the vertical line test. So your other part of your rational function would either go in this quadrant or maybe up here in this quadrant. But you'll never have them on top of each other because it has to pass the vertical line test. So when I draw a vertical line, I can only hit each of these functions once. And then graphs are always going to hug asymptotes. So when we start having asymptotes, your graph is going to approach it and then go along the asymptote all the way to infinity. So the first part I wanted to look at was just how to find the intercepts. So I'll do the first couple with you, and then maybe you can try these and then check your answers. So here's what you need to do. To find the y-intercept, plug in 0, just like we've been doing. To find the x-intercept, you're setting the equation equal to 0 and solving for x. But in this case, if you plug 0 in on this side of the equation, your first step would be to multiply the denominator to the other side. And we know that anything times 0 is 0. So really, it just ends up setting the numerator equal to 0. So numerator equal to 0 is kind of your shortcut. You're really plugging in 0 for y over here. You're really multiplying the denominator to the other side, but anything times 0 is 0, so you'll always get 0 equals your numerator. So the y-intercept, I think, is easier, right? You plug in 0 for x and see what you get. So you get 2 plus 0 over 0 minus 9. So what do you get for your y-intercept? Negative 2/9, right? And so to write a y-intercept, I plugged in 0 for x, and I have negative 2/9 as my y value. So that's my y-intercept. My x-intercept, all I have to do is set the numerator equal to 0, because it's like plugging in 0 on the other side, multiplying by the denominator. All I have left is my numerator. So I think you can see that x would have to be negative 2. So negative 2 comma 0 is my x-intercept. So let me do another one with you, and then I'm going to pause and have you try h and j for the intercepts. So on g, I'm going to plug in 0 everywhere. So 0 over 0 squared minus 9. And I know that 0 divided by anything is 0. So this would have a y-intercept at 0, comma 0. You don't want to leave it as 0/9 because 0/9 doesn't make sense. And so for my x-intercept, if all I have to do is set my numerator equal to 0, I already have my x-intercept, right? So if it has 0, 0 as a y-intercept, it kind of makes sense. It also has 0, 0 as an x-intercept. So here's what I got. So I plugged in 0 and got negative 5/8. And if you have a negative in the denominator, it just makes the fraction negative. If you had a negative in the numerator and a negative in the denominator, it would be positive, right? And then this one factored into x plus 5, x minus 1. So my two x-intercepts would be at negative 5 and negative 1. And then the denominator was undefined, so no y-intercept. The numerator was fixed at 1, so no x-intercept either. And so there we have our intercepts.